Well, thank you for the invitation to this important and very enjoyable meeting. My first contact with the work of Jean-Pierre Desmailles, I think, goes back to around 1985 with his paper on magnetic fields and Morse inequalities for D-bar cohomology. So magnetic fields, Morse inequalities, they seem to be two completely different subjects. So that was exciting to see how Jean-Pierre put these things together. And the paper was really an education for me in all the important ideas about the connection between complex geometry and the curvature of line bundles. And of course, although it's way above my head, at a technical level, I know that Jean-Pierre's work is fundamental in many of the advances in the study of Kähler-Einstein metrics over a long period. For example, in the work on the log canonical threshold that we heard about a few minutes ago in Robert Berman's talk. So it's a great pleasure to be here today. However, this talk is perhaps a bit different from many, but we're not talking about complex geometry. Bit disconcerting. What I'll be talking about, sometimes one thinks, oh, who took away the complex variables? But as I'll explain, there are many connections in the topic I'll be discussing with things that are perhaps more familiar to people in this audience. So what we're talking about, the context is the study of certain exceptional geometries in real dimension, well, in the general context of dimension 7 and 8, but we will only be talking about the 7-dimensional case, which is associated to the exceptional Lie group G2. So when we said these are related to complex geometry, these objects, which should be just saying more about, are very much akin to the study of Calabi-Yau manifolds. Or, from another point of view, the study of complex and also real Monge-Amp equations. Particularly in the case of, in the case of Calabi-Yau, this exceptional group G2, the place of that will be taken by the groups SUN. N is the complex dimension. So particularly, this relation is particularly true in the low-dimensional cases where n is 2, 3, and 4. So in a rather analogous way to which in topology the subject is divided into high-dimensional topology and low-dimensional topology, which has special features, there are some rather analogous features in complex geometry, which means there's sort of a special feature of low-dimensional Calabi-Yau manifolds connected to these exceptional geometries that we're talking about here. So I'm going to spend a good part of my talk, let's hope not the whole talk, reviewing some sort of standard foundations, the background material in this area, since I realize that the audience are not largely specialists in this topic. So review foundations. And the first part of this review is there's one a component from algebra, multilinear algebra. So you can think of this as in the same vein as when we look at the Monge-Amp equations. We put together an algebraic thing with differentiation. We either take a function and take, in the real case, it's Hessian of derivatives, or we take the complex, u alpha beta bar. We put this algebraic object and differentiation each by themselves, relatively straightforward, but when we put we get something interesting and more subtle. So the same sort of general ideas will be true here, and we want to begin with the relevant algebra. So let's consider a real vector space V of dimension 7, and we'll write lambda p for the exterior powers of the dual space. The basic construction that we want is the fact that if we have a 3 form, we have a phi in lambda 3, then there's a way to associate to this a volume form, i.e. an element of the top exterior power, lambda 7. Call it V of phi, and lambda 7. So how can we do this? There are various ways which could write this construction down. One way is to say we could consider a quadratic form on lambda 2 with values in the top exterior power, lambda equivalence. So we can take q phi, say, which maps lambda 2 times lambda 2 to lambda 7, just taking alpha and beta to phi wedge alpha wedge beta. And we get 2 plus 2 plus 3 gets us up to 7. So this is a line. This is symmetric bilinear form on a vector space. So in a standard way, this has a determinant which lies in another line. So in fact, this line will be the determinant line of, using a notation of determinant for the top exterior power, the determinant line of lambda 2 to the minus 2, because we're mapping it from this thing, tensored with this lambda 7 raised to the appropriate power. So tensor lambda 7 to the dimension of this space, which is 21. On the other hand, we can express the determinant of any, we can write the determinant of any exterior power as a suitable power of the determinant of V itself. So this whole thing ends up as being lambda 7 to a power given by the 21 that we have here, minus 2 times the relevant power is 6. So that's lambda 7 to the 9th. So since we're in the real case, we can take the 9th root of this object to get an element of this lambda 7. So Vi is equal to det q of phi to the 1/9. We'll give another definition in a moment. Another thing we can do is look at the variation of this thing with respect to a variation in phi. We differentiate this map from lambda 3 to lambda 7, and that will give us an element of lambda 4. So we can also get some psi equals psi of phi given by the variation infinitesimally of V of phi is psi wedge of infinitesimal variation in phi. So now suppose V is oriented. Now, let B be wanted. And consider the map which maps V into lambda 2, just given by the contraction of V. So if I map V into lambda 2, just taking V to the contraction of V with phi. And then we can take this quadratic form with values inside this line of volume forms, which has a sign. So we could say phi is positive. It's positive if this thing defines a positive definite quadratic form on V up to a factor. So in that case, for these set of positive 3 forms, we get a Euclidean structure, say G phi on our vector space, volume form this thing we defined previously, V of So out of our positive 3 form, it's an open set of 3 forms on a 7-dimensional vector space. Out of such a form, we construct a Euclidean structure, but most importantly, the volume form of the Euclidean structure. Another way of saying it is that this expression defines a conformal structure, a conformal class of Euclidean structures, and then we can normalize, we can fix the volume form by normalizing so that the norm of phi with respect to the corresponding metric is normalized to be some convenient value, like the square root of 7. In any case, this is the basic special 7-dimensional algebra that analogous to the algebra of the determinant that we want to exploit. And it could be expressed in various other ways, for example, in terms of Cayley numbers, and related to this exceptional Lie group G2, because if we take any positive 3 form, then the stabilizer of that under the general linear, in the general linear group of V is a copy of this exceptional Lie group G2. So that's the first piece of algebraic background, which of course is pretty incomprehensible. And what does it mean for this volume and the definition, perhaps, but it's definitely not clear immediately what the meaning of our definition is. But nevertheless, let's press on, and so consider the second part of background, so differential geometry. How are these related to special structures on manifolds? Supposing now we have a 7-dimensional oriented manifold and a 3 form on the manifold, which at each point is positive in the sense we've defined. Then we will get a Riemannian metric, G phi, and in particular a volume form. And also, another thing, we also get the 4 form we've defined here, psi, that we could, and also psi. So in fact, another way of describing this 4 form psi is given by taking the Hodge star of phi using the metric G phi. we wrote down the definition in terms of the variation of the volume function, but this is another way of representing it in terms of the metric. In any case, the point of all this is the following fact, that supposing these forms set are both closed, if d phi is equal to 0 and d phi is equal to 0, then this is the same equivalent to saying that the covariant derivative using the Levi-Civita connection of this metric of phi is 0, which is equivalent to saying that the holonomy group of this g phi is contained in G2. Being slightly imprecise, saying that this phi is covariant constant with respect to the Levi-Civita connection means that the phi is preserved by parallel transport, which is just the same as saying the holonomy group is contained in the stabilizer group of phi, which, as we've said, is this group G2. But we don't actually need to know about G2 for the purposes of this talk. All we need to know is that structures satisfying this condition are interesting and important things in differential geometry. For example, they give manifolds with zero Ricci curvature. Of course, the holonomy group in the case of Calabi-Yau manifolds, as we said, would be contained in this special unitary group, as mentioned above. Now, this is a basic result of Fernandez and Gray, this fact. The context for this talk is that we're interested in the existence of structures. We have a 7-manifold. When can we find a 3-form phi, which is positive at each point? This is an algebraic condition. It should be closed. Then also construct the 4-form made from the 3-form by some complicated algebraic procedure, and that should also be closed. If we can find such things, we get some very interesting Riemannian manifold. And we'd like to study this existence problem. And one way of thinking about this is in terms of a variational formulation. Due to Hitchin, which is well, we can think about the problem in 2 steps, because just knowing about a closed form is a relatively straightforward thing, because this is just something involving we can think of in terms of de Rham cohomology. Let's think of the problem in the following way: we fix a class, say C. Rham cohomology class, so we take some arbitrary closed form and look at all the ones that differ it by a D of a 2 form in H3 of MR. So we start with this closed manifold. So first question, does C contain a positive? Can we represent our given class by a closed form which satisfies this positivity condition? This is somewhat like we've got a corresponding question for symplectic structures. So supposing the answer is, of course, if the answer is no, we have no hope of finding one of these G2 structures. This what do we have over there? But suppose the answer is yes. So we have some subset, say C plus in C, consisting of all the positive representatives of our given cohomology class. So now we look at a natural functional on this set C plus, just given by mapping phi maps to the volume determined. At each point, we have a volume form, and we integrate that over M. So if we look at the variation of the volume function with respect to some infinitesimal variation in phi, by definition, that's given by the integral of taking the wedge product of the four form with our variation in phi. But now, if we're in the fixed cohomology class, so we write delta phi is equal to d of alpha, then this is the integral of psi wedge d of alpha, so we can assume working on a closed manifold, so we can integrate by parts and write the integral of d psi wedge alpha. This vanishes for all two forms alpha if and only if d psi equals 0, which is just the other condition that we want to solve. So the Euler-Lagrange equation is that d psi is equal to 0. So we can think of this equation as something relatively straightforward in principle in terms of, well, at least from the point of view of local differential geometry, expressed in terms of de Rham cohomology, and solving this equation as being find a critical point of the volume functional that we've defined. So we can ask these questions. We can start with a 7 manifold, and then we can fix a cohomology class. We can ask first, is this class represented by positive forms? And then, if so, can we find critical points of this volume functional on the space of volume on our space? And that would be very exciting if we could do that, but doing that goes far beyond the reach of what's possible in the present or in the foreseeable future. Moreover, we don't really have any, from what we've said, we don't really have any feel for what these objects are. We've sort of written down formal definitions, but it's not at all clear what is going on. So what we will do in this talk is just to discuss certain examples of this problem where we can simplify by reducing in dimension, mainly by imposing symmetry to get more to arrive at something more tractable and familiar. So we could say something about it. So there are examples of these, many examples of these closed manifolds with these G2 structures known, but they're typically big, complicated manifolds with numbers of often tens or hundreds or thousands or something. So one complication is that it's hard to see what's going on some big, complicated manifold. So to see something simpler, in this talk, discuss of the problem involving boundary value problems, where we don't need to just take our manifold to be a ball or something rather simple and still get some interesting PDE problem. Try to find the. That's it. So for that part, we're going to talk about variance involving boundary value problems. So our 7-manifold will have some boundary, a 6-manifold, and we fix phi restricted to the boundary of M. So to be a bit more precise, we will consider working with respect to some reference form phi naught plus forms of the form d alpha, where alpha restricted to the boundary of M to 0. More precisely. So we want to discuss really two different simplifications of the model where we reduce to problems in, well, ultimately both problems in 3 dimensions. And the foundation for these will be a basic algebraic model the situation of a 7-dimensional space with a positive 3 form when we split the 7-dimensional space into 3-dimensional and 4-dimensional pieces. So the 3 plus 4 dimensional algebraic model. We said when we take our 7-dimensional space, we will consider to be the form of U direct sum W, which has got dimension, which we're putting it, dimension 3. It's got dimension 4. And let's take yi to be, the expression of yi will be coordinates in our 3-dimensional space. So we're going to consider phi's of the form sum of omega I dyi, and the sign will work out, we're taking minus dy1, dy2, dy3, where omega I, so I is 1, 2, 3, are lambda 2 of the 4-dimensional piece. So for such special class of phi's, giving a 3 form is given by just giving a triple of 2 forms in 4 dimensions. The positivity condition then is just that the omega I span a maximal positive subspace in lambda 2 of W star, which we can think of as R33. In the sense, we think of this second exterior power of our 4-dimensional space is 6-dimensional. It has a quadratic form on it, up to a scale at least, it has a quadratic form on it defined by the product, taking omega goes to omega wedge omega. That quadratic form has signature 3, 3. The positivity condition for phi is that these 2 forms omega I span a maximal positive 3-dimensional subspace in this R33. And the connection with metrics is that this 3-dimensional subspace can be thought of as self-dual subspace for a metric on W unique at least by up to scale, because giving on a 4-dimensional space is equivalent to giving its up to scale is equivalent to giving its self-dual subspace inside the second exterior power. terms of the coordinate choice of coordinates yi and the components wi. More invariantly, the basic data we require to build such a form phi here is a map from U into lambda 2 of W star with image, mapping this with image a positive subspace for the wedge product form. So we want to consider two different reductions of our differential geometric problem based upon this 3 plus 4 dimensional splitting. We're going to, the reductions will be by imposing torus symmetry, and the two different cases will be whether we make the torus symmetry be in the 3 dimensions or in the 4-dimensional piece. First, I should mention that so these, if we have these subspaces with respect to a positive form, subspaces like this are referred to as associative, and the 4-dimensional ones like this are referred to as co-associative. So for the first function, we're going to consider a 4-dimensional torus on my 7-manifold preserving the 3-form phi in such a way that the fibers, the orbits of the torus action are going to be co-associative. So this is the situation that was studied by David Baraglia. So what we're going to describe will be essentially his work. So we have our formula. Phi is going to be the sum of omega I dyi. So our manifold M, we can take, it turns out to be essentially a product of a 3-manifold with this torus. In terms of local coordinates, our form is going to be of this shape. So the omega I are going to be constant coefficient on T4, but depending upon Y. So in the torus direction, these two forms are just constant coefficient forms, but they have some unspecified dependence at the moment in the y direction. So for any point P in y, then we have a map from the tangent space of y into the into this, what is more invariantly the H2 of the 4 torus. Because we're identifying the cohomology by taking the constant coefficient forms, which is our R33. And the of this map, so this is just the map that takes, at a point y, we take the span of these classes omega I. So the image of this map is a positive subspace here. So in another point of view, we have a map from y into the Grassmannian of three-dimensional positive subspaces of R33. Which we should think of, this space, for general purpose of generalization, as the Teichmuller space of flat structures on T4. Why? We have this flat torus, but that contains some structure which is encoded by the point in this Grassmannian. So the question then is for which forms phi of this shape will satisfy the condition. And the basic fact is that d phi equals 0 if and only if let's call this map, say, F. F is the Gauss map of some immersion locally of y into H2 of T4. And the other condition, the d psi equals 0, and only if the image is a maximal space-like submanifold. Yes, like this means that the tangent space of our submanifold is a positive subspace with respect to this indefinite quadratic form. Maximal means, by analogy with minimal submanifolds in Euclidean space, means that the submanifold is a critical point for the volume functional defined in the standard way for submanifolds of this space indefinite form. So the boundary value problem in this context, I will say if our manifold M now has boundary, but everything is preserved by this torus action, and we specify the data on the boundary, this is equivalent to the Plateau problem for maximal submanifolds in R33. So just the natural analog of the Plateau problem for minimal submanifolds will fix some two-dimensional submanifold in R33. We need to suppose that it bounds some space three-dimensional submanifold. This just corresponds to being able to solve the equation d phi equals 0, answering our first question. Then the question is, can we maximize the volume among all such submanifolds? Precisely the analog of the usual Plateau problem in Euclidean space. So this is an interesting and very natural problem in differential geometry. There are fundamental ways in which, in fact, this maximal problem in indefinite space, finding maximal submanifolds, is in fact somewhat simpler than the more familiar problem of finding minimal submanifolds in a Euclidean space. The changing the sign in the normal direction actually helps the problem. But this is, although there are many partial results known about this kind of Plateau problem, this is this is not, it's not known in general whether one can solve this problem. So there is a variant of this, which I was hoping to talk about, but time is running on, so I will not be able to, in which we replace this splitting into a 4 torus, where we consider a 7 manifold which is fibered by K3 surfaces, a manifold diffeomorphic to a K3 surface. And we replace this model in which we're considering flat structures on the by hypercalometrics on the K3 surface. And then one gets not quite an exact solution as here, but a solution to a natural adiabatic limit problem where the size of the K3 surfaces shrinks down to 0 size. But in the end, the problem is again expressed in the same way in terms of finding a maximal submanifold, but again, now not in R33, but in the cohomology of a K3 surface in R319. But obviously, I don't have any time to explain more about that. Just to say, this kind of reduction to a 3-dimensional problem goes beyond this rather special situation we've considered of the torus actions, and also there are global variants of the situation where we consider fibrations of singularities and structures that actually occur in many known examples of compact manifolds. But let's just, in the last few minutes, go on to the other situation. So the second reduction. So now we can say E3 acts on M phi with associative orbits. So we take our same formula the y's are just coordinates on our flat 3 torus, and the 3 forms omega, the triple of forms M is T3 times X, so omega I are 2 forms on X. So we have a problem for a triple of 2 forms on X, and we can express them the following way. The condition phi 0 is that the d of omega I equals 0. The volume form in this situation is given by the following. By the following. Take, so out of a triple of 2 forms, omega 1, omega 2, omega 3 on our 4 manifold, we construct a volume form. Well, we write it down as the following expression. In a sense, if I take any reference volume form, chi 0, then I can interpret the products omega I wedge omega j, dividing by chi 0, get those as numbers. I can take the determinant of that 3 by 3 matrix to get a number and take the third power. Then I can multiply that by chi 0. But from the fact we put this third power in, if you change chi 0 by a multiple, the multiples will cancel out. So this is actually independent of chi 0. So our variational problem in this reduction becomes just to look at a triple of closed 2 forms on our 4 manifold. We have the function given by this determinant, and we're looking at the integral of chi. This is the volume function. Then so what are the Euler-Lagrange equations? They say we take another triple of 2 forms, theta I, equal to the sum of, say, lambda ij omega j. So lambda ij is the inverse of a matrix, well, the matrix given by omega I wedge omega j over chi to the minus 1. So from one triple of two forms, we produce omega 1, omega 2, and omega 3. We produce another one, which is essentially a dual basis, a dual triple. And that the Lagrange equations is that d of theta I is equal to 0. So this is an interesting reduction of our 7-dimensional problem to 4 dimensions. We have a question involving triples of 2 forms. Notice there's a sort of an element of mirror symmetry here, in that, or symmetry here, in that there's a symmetrical relationship in the end between the omegas and the theta. If you took the thetas and applied the same procedure, you get the same procedure would generate the omegas. So that's one reduction. So just in the last 2 minutes, we could describe another. We can describe a further reduction to 3 dimensions. It should be rather brief. So let's just say reduction say 2 plus. So we consider, so in a S1 action on X, which is Hamiltonian for each of the omega I. We have Hamiltonian functions hi from X to R, the Hamiltonians. Another way, we could say we have a map from X mapping to some open set U in R3. If we put together these three Hamiltonian functions, and let's suppose that this is an S1 bundle, principal S1 bundle. So then the corresponding thing is that the data is in terms of a connection form, say A, for this circle bundle, a one-form X, and a matrix-valued function sigma ij, matrix-valued function on U. So we consider the forms of the shape omega I is dxi wedge A plus sigma ij, so the summing epsilon jkl dxk dxl, where you're taking x1, x2, and x3, the standard coordinates on R3. So finally, in this way, we can also use the equations to eliminate the connection. And finally, we arrive at equations for this data given by a matrix-valued function, 3×3 symmetric matrix-valued function, sigma, on an open set U in R3. So I'll just write down the equations that arise, and then I will stop. So the equations are, and the solution to the equations is that sigma ij is, say, V times uij, where U solves the Monge-Amp equation on U, on our open set in R3, the determinant of uij is equal to 1. Uij is the inverse of the Hessian of u, and v satisfies the linear equation the sum of we take the, in fact, this is the natural second order linear equation, which is just the linearization of the Monge-Amp pair equation at the solution u. So this reduction of our 7-dimensional equations finally comes down to being, for a pair, solve the 3-dimensional real Monge-Amp pair equations, and it's the linear equation. So I was going to say something a bit more about it, but I run out of time, so I should stop at this point.